submitted to the special ANA issue on Rosetta using the MIRO, or microwave instrument, for the Rosetta orbiter. You know, one of the things I thought is that, you know, since we're on YouTube, you know, I felt somewhat obliged to show a video of a cat or a puppy or something. Problem is I have way too many slides for that, so you just have to make do with a picture of a cat and a puppy. So what I'd like to do is tell you a bit about the MIRO instrument and some of the features of our data. Since this is an infrared crowd, things are a little different at longer wavelengths. Then I'd like to tell you about two approaches to analysis of the data, fitting diurnal phase curves and also fitting directly a thermophysical model. And finally show you some maps of the residuals, which are interesting. And then hopefully make some conclusions. So the MIRO instrument, MIRO is a millimeter wave instrument. So it's a very long wavelength compared to what we're used to thinking about in this group. Here's the instrument located on Rosetta in the thermal vacuum chamber. It's a 30-centimeter off-axis parabola telescope. And there's two channels for the continuum observations. This thing we call the sub-millimeter channel, which is at about 0.5 millimeter. And the millimeter channel is at 1.6 millimeters. During the data I'm going to be showing you, the resolution for the sub-millimeter channel is about 65 meters on the nucleus, and it's about 3 times that for the millimeter channel. So now, MIRO, by being a millimeter wave instrument, has some special properties. The first thing to keep in mind is that at these wavelengths, our signal is linearly proportional to the brightness temperature. And one of the features of that is that there isn't any of this beaming stuff that I've been hearing about for the last couple of days going on as a result. The other thing about MIRO is we don't look at the surface, we look beneath the surface, which is why we go through millimeter wave detectors when you go through the airport. Over here is a plot of the weighting functions for two wavelengths, basically separated by a factor of 4 in absorption coefficient. And basically you see down to something like the point where the optical depth is approximately 1. The interesting thing about these weighting functions is if you're used to looking at atmospheric weighting functions, which maybe nobody in this group is, but when you do atmospheric sounding, the atmospheric sounders pick frequencies and pick out particular layers in the atmosphere. In this case, basically, we do an integral over depth, and so we see emission from all of the same places particularly up near the surface in both channels, right? So it's not like we see down here and we, you know, and are at the longer wavelength. We see everything at over the whole thing. It's just that the weighting is a little different, so that you get to probe a bit deeper. Now, our information in this data is in the diurnal variations of the emission. But one of the features of MIRO is that we don't sit and look at one spot and measure a whole diurnal phase curve. We have to build that up by looking at basically similar spots at different times of day and then try to do our fitting. And I'll show you how that works. So here's just an example of a map. The observing sequences, sometimes we're able to produce, we were able to produce maps. We would do little maps. As you do these maps, you have to be very careful because the nucleus is actually rotating underneath you as you do the map, and that makes it actually pretty hard to turn our data directly into maps. But here's an example of when we were able to do that. Over here is a map from the sub-millimeter channel. You can see there's quite a bit of structure. You can see that in the scans that we go across here. Sort of things that you see are that the temperature goes down as we go from this area on the nucleus, which is the higher latitudes, down to the lower latitudes. So there's a seasonal dependence that's important. And then there's a lot of features in here. And the features are always correlated with basically local slopes and topography and places where there's shadows. In fact, this big hole in the emission correlates pretty well to a region next to a wall where there's a shadow. Because of that, and because the nucleus geometry is so strange, we do everything in terms of what we call effective latitude and longitude. That is, we look at the surface normal of a local spot in order to define what its orientation is with respect to the sun. And that's what we mean by effective latitude and longitude. All our modeling, we require the use of a digital shape model, which is why I have all those OSIRIS people on the Miro paper. But that works out pretty well. One of the other features of all this is that there is a roughness, if you like, effect on Miro, which is that within our beam, our antenna beam, we're looking at surfaces with different orientations with respect to the sun. So there's some kind of averaging over those surfaces, and this essentially we think adds something like noise or random noise to the model fitting. So the analysis, the data I'm going to be telling you about is from way back in September 2014. The typical distance to the nucleus was about 30 kilometers. I have about 200,000 observations for each wavelength channel used in this particular fitting. And we did two things. We fit phase curves to different bins of effective latitude, and then we also fit a full thermophysical model. So I thought I ought to show some equations. Basically, this is to motivate, just what it is that we see when we look at millimeter wavelengths. And if you want to study up on this, just go back and look at what radio astronomers were writing about the moon in 1960. So we have the heat equation, which everybody knows, and we all know that you can expand the surface temperature and use that as a boundary condition if you expand it as a Fourier series. And then there's a well-known solution with that as the boundary condition for what goes on below. And basically, you wind up with each of these components being attenuated and shifted in phase as you go deeper into the interior. And the important parameter there is the thermal scale length, which we've already seen defined, which we think on CG is about 1 centimeter. So then to compute our observables, you actually have to do an integral over over all depths, weighted by the absorption. If it's constant over depth, then you can do that integral for those Fourier terms, and you get this mess here. And basically, what you see is that the amplitude of the surface harmonics is reduced by this particular factor, which involves this parameter called delta. And delta is basically the ratio of the length into the surface that you see divided by the thermal scale length. So if you see many, many, many thermal scale lengths, delta is really big. If delta is really big, then this term becomes really small, right? On the other hand, if it's smaller, then this term can approach the surface temperature value. The other feature here is in the phase. Over here, the phase lags of the peak at the radio wavelength lags behind that of the surface by some amount, up to 45 degrees, in fact. And that also depends upon this ratio of absorption length to thermal length. So as that increases, the amplitude of the observed brightness temperature change decreases, and the phase lag increases. And we can use that all to figure out what this ratio is, just from the phase curves. Okay, so I'm going to be showing you data we fit. The two kinds of fitting, we've used two boundaries here on the nucleus for internal team reasons. The phase curves were fit to the solid line region, and the thermal physical model is fit to the dotted line region. And for those not used to looking at CG in latitude longitude space, so this region of longitudes, and this one corresponds to the head. The region we're looking at corresponds to the body, basically like the bottom of the duck. And then the region in between is the neck. Okay, so here's some examples of fitting phase curves to the data. We don't get uniform sampling at all latitudes of the measurements with phase, but we do pretty well, and we're able to define the phase curves. And one of the features is that the amplitude of the submillimeter channel variations is bigger than that of the millimeter variations, and the phase of the millimeter phase curve is delayed compared to the submillimeter one. And this is exactly what you would expect from these thermal waves propagating into the interior. So let's look at some of the results of the phase curve fit in a little more detail. Here is a plot of the mean brightness temperature as a function of the effective latitude for the millimeter and the submillimeter data. What we see is that there's a difference between the submillimeter and the millimeter mean brightness temperature. Now, most of this, and we're still debating how much, but possibly all, but most, I would say, is due to an effect of our instrument, something called the beam efficiency of the telescope. The surface of the telescope has errors that cause the shorter wavelength efficiency or to be less than that of the longer wavelength efficiency. The expected ratio is about 0.94 for that effect. And over here is the plot of the ratio of the submillimeter, the power we see in the submillimeter channel to the power we see in the millimeter channel versus the signal in the millimeter channel. These curves have to do with the Planck function and stuff like that. So, but in any case, you can see that we get a kind of a typical ratio here, and that typical ratio is somewhere around 0.94. So in fact, we think that at least some and maybe of this difference and maybe all of this difference can be accounted for with the beam efficiency. So to make things simple, for this work, we've just assumed that that's the number for the beam efficiency, and this is something that we're going to have to keep working on because it would be very interesting if there were actually a difference between the two wavelengths in the mean temperature. Then here's a plot of the amplitudes of the curves versus the effective latitude. And you can see the bigger amplitude for the submillimeter to the millimeter channel. We can plot the ratio of those amplitudes versus effective latitude, so ratio of millimeter to submillimeter, and compare that to that simple model I showed based upon what the value of delta is, the ratio of absorption length at submillimeter to thermal length, assuming a particular ratio, which is the one that you see on the moon at these wavelengths, about 4 between the millimeter and the submillimeter channel. And you can see that these are pretty consistent with a single ratio, and that single ratio is a little bit less than 1, something like 0.7 for the submillimeter channel. We can also look at the phase. This is a little more interesting, although a little noisier because we don't have such great sampling of the full range of phase for all latitudes, and that's reflected in these error bars. There's some places where we get really good sampling, and so the error bars tend to be small up here. If you look at the difference in the phase between these two and compare that to the expectation of that simple model that I showed you before, you can see that particularly where we have really good phases, but really across the board, the difference in phase between millimeter and submillimeter is a bit different than you would expect from that same set of models that I showed. And in fact, there's no way that that set of models can produce the phase difference that we see between the millimeter and submillimeter channels. So now that set of models assumes a homogeneous surface, and my thought is that this phase off difference may be evidence for some kind of layering in the structure of the near subsurface. Okay, so let's move on and look at the other way we analyze this data, and that is by fitting thermal models to the data. So our approach here has been, we have a thermophysical model. It's the model that Steve Keim, my colleague, has been developing for years and was applied to the Lutetia data and so on that was published before. The strategy here is to adopt values of various parameters which we think we know reasonably well, or in any case are not as likely to be as variable as the thermal inertia in the case of the model. So we adopt a value for bond albedo and density and specific heat and infrared emissivity, and then we use the thermal model to solve for the best fitting thermal inertia and the best fitting absorption length at the two wavelengths. So this is that's two parameters, so we can draw up the chi-squared as a surface, and find minimum. And so here is the submillimeter chi-square surface and the millimeter wave channel chi-squared surface. And you can see that we have a well-defined minimum here. Interestingly enough, the thermal inertia comes out to be approximately the same at the two wavelengths, which are being fit independently of each other, and the length into which we and the absorption length. And then in this case, it turns out to be about 1 with some error, and between 3.5 and 4 in the other case. We find that if you change these values around, things don't change by very much. So, I think that the result is pretty robust. Some features of the model is that they are, as in the other case, they're all homogeneous models. There's no layers or anything going on in here. And another feature is that the models don't, because they were developed for the moon and asteroids in the years before asteroids had sublimation. They don't include any sublimation. Okay, and I've just added that to the model, and I can tell you a little about those results, but I don't really have anything I'd care to show in public. All right, so these are the formal fits. These are the adopted values. In this case, we just adopted the bulk density for the comet as our density. You can argue that maybe it should be less, or some people would argue maybe it should be more. As I say, if you change the specific heat, basically correlates really well with the density. So we would basically model these two together. And so if you change the density by 50%, you don't change the result by very much. Is the thermal inertia values that were fit in this case, and then the ratio of absorption length to thermal length, which is the other thing that we determined pretty well. The fit RMSs are a bit high compared to what we think the noise on the data should be, and that's simply, we think, because we're having within the beam there are facets at different orientations. It kind of, well, I've worked models of this. It kind of works out that because the submillimeter beam is smaller and the effect of the geometry is greater, that you might expect that there would be a bigger RMS because of that, and well, anyway, there is. So in the end, we can derive from these fitted values what the values of the thermal scale length is, and it's about 1 centimeter, and the ratio of the two is about 4, which we were happy about because that's about the number that you get for the moon. So now it'd be interesting, let's see how they compare to those phase curve results. The phase curve results are completely independent of a thermal model. Okay, and so here's the results, the best fitting model, which is the one for I is equal to 22 here, versus effective latitude compared to the phase curve results. I've scaled all the submillimeter points by this 0.94 factor, and you can see that we match pretty well, except at the highest latitudes up here. At the highest latitudes, we think that this is a result of sublimation occurring, and that's something I've been able to confirm now that I've added sublimation into the model. Here's how things vary. Here's how the amplitudes of the first harmonic of the phase vary. The solid line is the best fit from the thermal model, and then these represent kind of 1 sigma error bars on the thermal parameters that go into that. You can see that basically the behavior that we saw with the phase from the phase curves directly is reproduced here. The value that we got for the ratio of the absorption length to thermal length of 1 in the formal fit is pretty close to the 0.7 that we got, and probably, I think, within the errors, although Emmanuel likes to argue with me about that. And the ratio of the two is consistent with what we were using to interpret the phase curve. So I think things are generally in pretty good agreement there. If you look at the phases of the thermal model, so these are the predicted phases for the thermal model, and you can see that the difference in the observed phases of the phase curves is quite a bit different than the difference in the phases from the thermal models. And again, this I think may have something to do with vertical structure within the upper centimeters of the surface. Okay, so I think the next thing that I'd like to do is to talk a bit about mapping the residuals. One of the things when I came into this, I was imagining I was going to make these glorious full color images of the comet and really wow everybody. But it turns out that that's just impossible to do the way we sample the sample of things. So what we need to do in order to make glorious color images is we have to do that in the context of a model. And so what I'm going to show you is some results of simple fitting, basically what we see when we look at the residuals to a model mapped over the surface. You know, I'm stuck with that because basically of the sampling problem. Okay, so in this case, what we're doing is we're looking at the residuals to the thermal model. It turns out that pretty much you might imagine that since you're looking at different times of day for every single observation, that it'd be a big complicated mess. But pretty much what happens as you change the thermal inertia is it shifts the curves up and down, so that the residual that we see, if it's positive or negative because of a thermal parameter change, is the same over the whole phase. So in fact, looking at the residuals that way is not a crazy thing to be doing, although I hope to get more sophisticated about this. Okay, so let's take a look. We're going to just look at the submillimeter channel because it's the higher resolution channel, and it's pretty hard. It's pretty hard to figure out how to display this stuff on this complicated surface. So what I've done is I've taken the residuals and I've mapped them onto a projection of the comet. So in this case, we're looking. This shows what the geometry is. We're looking, and this is all deduced from the shape model. The shading here is proportional to the illumination, the solar illumination of the surface. So the places that are white are places that get a lot of sunlight averaged over a rotation, and the places that are black get no sunlight. That's also coincidentally where the shape model we're using doesn't work is completely unknown, so that's a bit of a problem, but because nobody could look at it. But in any case, here we are, we're looking at the part where we actually did the fitting. Then over here on the right, these various color contours show the residuals. And what's interesting about this is actually that it's kind of uninteresting. There aren't a lot of residuals where we did the fitting, right? So there's a few places that stand out. In fact, so here's a big positive and some big negatives, and that corresponds to that feature that we saw in the very first map I showed you. You're looking at a place that's heavily shadowed by a cliff right here. There's also this part down here, which I'm going to tell you not to worry about because we have no idea what the shape of the comet is down there, and so I have no idea how to compute what the thermal model really ought to look like. If you look up here at the top, at the higher latitudes, you can see these are mostly negatives, and that's this phenomenon that we saw in mean temperatures before, which I think is largely due to sublimation. Here's another view. So basically, before we were looking end on at this thing. Now we move up a little bit and make a map. Again, the region where we did the fitting, the residuals are pretty small, but we get some rather bigger residuals up here on the top where there's a lot of sunlight, and I think because a lot of sublimation, that lowers, we get negatives at that point. And then compared to the model, this one wall at the bottom of the head is a rather big positive residual. You notice that the top of the head is like the top of the body here, and the solar illuminated part, that's where we see big negative residuals, which again I think is due to sublimation. Oh, I should say this shows the coverage of the samples on the map down here. Each point, each observation is a yellow point in that yellow mass. Turn around and look at the head. Okay. turn around and look at the head. Again, I'm not going to worry too much about this stuff down here because we don't really know what the shape is. And but the head, basically, there are not big residuals. We didn't fit this part, but the fact that there are not big residuals, it indicates to me that basically the same thermal properties must work there as well. And we see the big negatives at the top where I think sublimation is going on. Then finally we look up, sort of back the other direction. That's kind of interesting. Again, the negatives on the other, let's say, wall of the neck. We have some big positives. There's an interesting feature here on a feature called Seth in the by the people. So this is basically a pit or something, and at the bottom is a very big negative, surrounded by little positives, and then here along the walls we have these positives. Now, why the big residuals along the walls? Well, and sort of to summarize that, here's a view from the pole. We have these big positive residuals along the walls. Why would that happen? Well, this is in fact one of the more complicated places in terms of the illumination of the comet. So here at a time that's supposed to be day, on this wall, we're getting a shadow cast by the head on the wall of the comet. So all the phases and all of the rest of that stuff that goes into the thermal model are completely wrong. So maybe it's not surprising that we get some big residuals there, and similar effect over on the other wall. So there's various reasons why we have residuals. As you saw, the places where the shape model is not well determined sometimes appear with large residuals. There's shadows that can complicate the illumination and lead to larger residuals. Sublimation, I'm pretty sure, leads to the negatives at the tops. There's self-heating and things. We haven't included any of that stuff in the models yet. And then finally, there could be variations in thermal properties, though at the moment I'm inclined to think that most of the differences that we see are just due to, let's say, imprecision, or most of the residuals are due to topographic problems as opposed to properties. Okay, so the conclusions: thermal models are consistent with low values of the thermal inertia between 10 and 30, let's say. The details of the phase curves are somewhat suggestive of some vertical structure in the near layers, and that's something we got to work on. The properties, I think, are pretty uniform over the whole nucleus, and with sublimation being important. And then finally, we've just scratched the surface of all of this. We're back in September, and we've got months and months and months of data. So, thank you.
Thank you very much, Pete. Questions?
Yeah, I have a quick one. You sort of alluded to it already, but I wouldn't be surprised if your positive residuals in the neck were really self-heating, photons bouncing back and forth from one side of the neck to the other. That would drive your temperatures up easily.
Yeah, well, there's a lot of things that it could be. I mean, that's one. I mean, another is that, one of those walls looks like a cliff. So I mean, it could be that the thermal properties of the cliff are a little different than most of the rest of the area, maybe. And then there is this complicated illumination pattern that may lead to, but yes, self-heating is certainly something we've thought about, and that's a good one to, it's going to be a mess to model that.
This is really neat stuff, and I'd be really interested to see the sublimation results too. But just to comment, I was surprised you use a constant heat capacity, whereas we know from experience with the moon that varies by at least a factor of 2 over the temperature range that you're looking at.
Well, no, I mean, we're down at, typically 150 or something like that. So
the conductivity won't vary in that temperature range, but the heat capacity will.
Well, I'll take a look at that.
Okay.
Questions?
I have two fundamental questions. guess the first one is the temperature you are showing in all the curves. How can I define them in physical sense? I think there's a mixture of different fluxes from different depths and a kind of brightness temperature, whatever, but not a kinetic temperature that I would need for thermal models and so on. How can you close this gap between brightness temperature and the physical one, the kinetic temperature? Is the first question. And the second is more hobby of me, this well-known parameter thermal inertia. I like it, but we should be aware that it's only defined on the surface. So thermal inertia is only, from its history, from its definition, only defined directly on the surface. And to talk on a thermal inertia below the surface is not reasonable in a mathematical and physical sense. But it's also what you must do here, because you have layering and all these things. But for me, it's dangerous to mix this parameter with properties and steps. What's your idea?
Okay, so let's see, part one. So we measure the brightness temperature. So the brightness temperature is defined as the temperature that a black body would have to produce the flux that we observe in our beam. So now there's various reasons why that wouldn't be the same as the physical temperature of the surface. One is that I didn't point at it explicitly, but there's a surface emissivity that we have to worry about. That we think is pretty close to 1 because the dielectric constant is pretty close to 1 as measured by CONSERT. But it's not exactly 1. So if one wanted to, you could make a small correction for that. But there's other effects that could influence things as well. And then it's true that we, basically, as I tried to indicate in the one slide, we get the, let's say, a weighted average of the physical temperature below the surface. So, we're never going to be able to say that at such and such a depth, the temperature is X. I mean, it's always going to be a weighted average. And if you're interested in comparing it to models, you're going to have to do the weighting that we do. The second point, I guess we just define the thermal inertia as the square root of the conductivity times the specific heat times the density, and because that's a common way that people intercompare values.
Why don't we have this debate?
Yeah.
The fundamental one this afternoon in discussion, because we have to.
Yeah, we could report equally obscure numbers for the thermal conductivity.
Okay, so next talk by Cedric Lera about surface thermal properties inferred by Regis and Rosetta.
Okay, so